conditions cannot be determined by simple calculation because the amount of relaxation is unknown and cannot be judged reliably. It depends in a complex way on the metallurgy, pipe route, anchors, location, and geometry. However, the service failure are related to cyclic rather than static condition, and it is therefore permissible to assume that the system will operate satisfactorily if some of the hot and cold stresses is within a stress range which is considered safe for an expected number of stress levels. This concept provides a logical basis to design a piping system because it takes into consideration system all the stress levels to which system is subjected. The actual stresses intensity at a specific stage is of academic interest only. Till now we are discussed and we are elaborated here the constraint points. Here is a A, another is a C, and later the expansion. So then C becomes C dash and A becomes A dash. And later points B will expands terms of B dash, B2 and B3. It could be seen that the core recognition, the fact that the stresses in piping systems are not necessarily of constant intensity, that the expansion stress at elevated temperature may not be sustained because of relaxation or creep, and consequently will drop to stress level the material can sustain. The phenomena of yielding in the elastic range or flow in the plastic stage presents a problem different from that encountered in the analysis of structure which operates at relatively low temperatures and therefore in a state of steady stress. In this case, the elements are designed to meet the limiting stress or deformation within the elastic limit of the material. In contrast with the stresses from sustained loads, which the internal pressures or weight, the displacement stress can across the elastic limits. We stress a reversal from cold to hot condition and still remain safe, provided the number of stress reversal remain below the limit to exclude the possibility of failure due to fatigues. While stresses resulting from displacement strain diminish with time due to yielding or creep, the algebraic difference between strains in the extreme displacement condition and the installed condition remain substantially constant during any one cycle of operations. The difference in strain produce a corresponding stress differential, the displacement stress range, which is used as the criteria for designing a piping flexibility. The type of cyclic straining described, if repeated often enough, with all cause the pipe to crack. The cracking will start at the point or points where the stress is maximum. This is what mean by fatigue failure. A average axial stress over the pipe cross section due to longitudinal force caused by displacement strain are not normally considered in the determination of displacement stress range since these stresses are not significant in typical piping layouts. In special cases, consideration of average axial displacement stress is necessary. For example, include buried lines containing hot fluids, double wall pipes, and parallel lines with different operating temperature connected together at more than one point. See here at point A and C, it's connected more than one point. Now we'll see the effect of fatigue on pipings. In effect of fatigue on piping, here, as per the Merkel instigation, the phenomenon of fatigue failure of piping during 1940s and 1950s. He tested a number of configuration straight pipes, various fittings such as elbows, miter bands, welding tees, fabricated tee, etc. Mostly on 4-inch NB size, that is nominal bore size, by using cyclic displacement to apply alternate bending stress. The plotting the cycles to failure for each applied displacement, he found that the results were on the expected lines and followed the shape of fatigue curves. Then Merkel observed that the fatigue failure occurred not in the middle of his test span but in the intensity of fatigues and also at lower stress or cycle combination than for the straight pipes. This leads to what is called the stress intensification factors, which covered in under section 5.3 in ASME 31.1. And next is time dependent stresses. What does mean the time dependent stresses? When we are considered different kind of the fatigue pipings, the stress intensity factors. Now, if an initial applied displacement, if you consider the initial applied stresses, the fatigue on pipings. Therefore, we have to consider the applied load displacement causes the pipe to yield. It's a result in plastic deformation and producing the pre-stress in the system when it is brought back to its original state. By withdrawing the load, this pre-stress must be overcome by subsequent stress application, resulting in lower absolute stresses during later load cycles. Because of this expected system relaxation, the initial thermal stresses are allowed to exceed the thermal stresses and are allowed to exceed the material yield stresses with the aim that the system self-spring during the first few cycles and then settles down into elastic cyclings. The reason for this allowable overstress is that a repeatedly applied load, which initially forced the pipe into plastic range, will after a few cycles, it's called as shakedown and reduced to elastic action in the piping systems. This theory can be understood by considering a pipe experiencing an imposed displacement which is beyond its yield strength. When cyclic displacement is removed, the piping component which exceed the yield point and will retain the residual distortion equal to imposed strain yield strains. This distortion will induce yield stress opposite in sign to that developed during loading and equal to difference between the calculated stress value and material stress. The range has been extended by the value of this pretest. Now, next is allowable stress. In allowable stress, the American piping codes cover under ASME B31.3 subscribes to failure of piping system to the basis of maximum principal stresses theory. I think we have studied what is maximum principal stress theory in machine drawing. And the theory states that the yielding occurs when the magnitude of any of the three mutually perpendicular stresses exceeds the yield strain of the material. Temperature and pressure are the significant factors governing the stresses created in the piping systems. There are other factors that influence the stress. Now, which the other factors? First one is wind loads, smoke loads, relief wall force, fluid hammer, settlement, equipment vibration, weight of attachment, and weight of contents. These are the factors that influence the stress. All these factors contribute to distinct form of stresses. The sustained stress generated by pressure, dead weight of contents and attachments, which can be expected to be present virtually at all time of plant operations. The self-limiting stresses generated by thermal effects. The allowable stresses for these two influence are based on different concepts. However, the allowable stresses specified in code are based on material properties. They can be classified into two categories. So first one is time dependent stresses and second one is time dependent and independent stresses, and they are defined as per ASME 31.1 and ASME 31.3. Now we'll see time independent stresses and time dependent stresses. Time dependent stresses, the yield stress is the elastic limit, and that is the value below which the stresses are proportional to strain. And when the load is removed, there is no permanent distortion. The ultimate tensile stress means here UTS. That is nothing but ultimate tensile stress, and YS is yield stress. The ultimate tensile strain is the highest stress, which is the specimen can accommodate without failure. The basic allowable material stress at hot operating or design temperatures. That is, we can define SH, that is hot temperatures, is defined by the code as minimum as per the ASMEB 31.31.1. This defined as per the code ASMEB 31.1, and in this code, 1/4 of the ultimate tensile strength of the material at operating temperature and 1/4 of the ultimate tensile strength of the material at room temperature, and 5/8 of the yield strength of the material at operating temperatures. 90% of the yield stress for acoustic stability and 5/8 of the yield strength of the material at room temperatures. Means 90% of the yield stress for a stick stainless steel and 100% of the average stress for 0.01% creep rate per 1000 hours. Now next code, that is AB 31.3. So as per this code, the 1/3 of the ultimate tensile strength of the material at operating temperatures and 1/3 of the ultimate tensile strength of the material at room temperature and 2/3 of the yield strength of the material at operating temperature. It means 90% of the yield stress for authentic stainless steels. Next, 2/3 of the yield strength of material at room temperature. It means 90% of yield stress for authentic stainless steels and 100% of the average stress for 0.01 Cre at a rate 1000 hours and 67% of the average stress for rupture at 1 lakh hours. 80% of the maximum stress for rupture after 1 lakh hours. It's the basic allowable material stress at hot temperature is defined by the code ASME B 31.1 and ASME B 31.3. So as per this code, we can consider their particular range, the materials. Now we'll see the time dependent stresses. Time dependent stresses, so allowable stress is based on either yield stress or the ultimate tensile strength, material measured in simple tensile states. Might be you perform, you test in strength of material, find out the ultimate strength. The time of performing experiment in strength of material under the subjects, we perform the kind of stresses, ultimate stress and yield stresses when we pick the different materials or specimens. Based on that, we are discuss these two codes, ASME B 31.1 and ASME B 31.3 for time dependent stress. Now next is time dependent stress. Here we discuss the time independent stresses. Now is time dependent stresses. Time dependent allowable stress is usually related to the creep rupture strain at high temperature above 1/3 of the melting points. Most metals will exhibit creep in standard tensile tests if the load is kept constant. The specimen will continue to deform with time. Under constant load, the rate of creep strain will decrease initially to a steady state and later will increase rapidly until it fails due to creep ruptures. The code use an allowable stress, which is the smaller time dependent and time independent allowable stress. The time dependent allowable stress is the smallest of 67% of the average stress to cause creep rupture in lakhs hour, 80% of the minimum stress to cause rupture 1 lakh hours or 100% of the stress to give 0.01% of creep rate per hours. And the self-limiting stress, which one is self-limiting stress in piping system are essentially cyclics and the initial hot stresses, if they are of sufficient magnitude, will decrease with time because of the plastic strain and will reappear as a stress of reverse direction when the pipe cools. This phenomenon forms the basic difference between self-limiting stresses and the sustained stresses. Now, the degree of cells springing, as a slain in earlier lectures, will depend on the magnitude of the initial hot stresses and the temperature, so that the hot stresses will gradually decrease with time. The sum of hot and cold stresses will stay the same. The sum is called the expansion stress range. This leads us to the selection of an allowable expansion stress range. Self springing occurs only when the system is subjected to higher temperature. For the expected strain, means expected expansion per unit length, if the modulus of elasticity at this temperature The high is used to back calculate stress. The stress will be lower than when it is calculated using modulus of elasticity value at lower temperature, means at cold condition. That is, calculated stress value is higher when material properties in cold condition are used. This provides a built-in safety in designs. Hence, the stresses are calculated using cold modulus of elasticity. This is very important point to note. The actual stresses under hot condition would be less than the calculated stresses. When difference in elastic modulus within the piping system will significantly affect the stress distribution. The resulting displacement stress shall be computed based on the actual elastic modulus and then multiply by the ratio of the elastic modulus at the ambient temperature to the modulus used in the analysis. There are other failure modes that could affect the piping systems. They include bucklings, stress corrosion, and brittle fractures. These are not necessarily considered in the piping codes. These points are not considered in the piping codes. The effect of these must be considered by the piping engineer while selecting the material or restraining the piping system. Now, next is allowable stress range. So, here can see the allowable stress range. So, this allowable stress range failure modes that the piping code address are excessive plastics, deformation or bursting, plastic instability or incremental collapse due to cyclic in the plastic range, and fatigue, which may be developed in a system as its temperature is raised from the lowest to the highest that will experience in service or when it is shut down. Each of these failure modes is caused by a different types of stress and loading. However, fatigue failure is recognized by the code as most likely mode of failure of the components and place the limit on the maximum stress, which may be developed in a system as temperature is raised from lowest to highest that will experience in service or when it is set down. This piping shakedown is also known as self springing and can be represented in through this sketch. Here it is represented this piping shutdown or we call the self springings. The maximum stress range may be set to 2 times the yield stress. More accurately, to run off hot and cold yield stress in order to ensure actually elastic cycling within the bonds of allowable stress, incorporating a factor of safety. This can be represented by the help of this relation, that is SE less than equal to F in bracket S of YC plus S of YH, where here S is nothing but expansion stress range and F is nothing but factor of safety. SYC, that is yield stress at installed temperatures, and Y that is yield stress, YSH, that is yield stress at operating temperature. And through this relation can calculate the factor of safety. It's a relation for material below the creep ranges. The allowable stress are 62.5% of the yield stress, so that a conservative estimate of the limit the bending stress at which plastic flow starts at an elevated temperature is 1.6 times the allowable stress. And by the same reasoning, 1.6 in this equation here, 1.6 and 1.sh and AC for the yield stress at install temperature and yield stress at operating temperatures. So we have to consider the sum of these stresses represents the maximum stress range to which the system would subject it to without the flow occurring in either hot or cold conditions. Therefore, we have to consider the maximum stress range, that is 1.6 into S of C plus 1.6 into S H equals to, if you simplify this relation, so here 1.6 is a common term. Then in the bracket we can write S of C plus S of H. But the American design code means ASME 31.1 and ASME 31.3 limit the stress range to 78% of the yield stress, which gives a total stress range here with the help of this relation. So it gives the total stress range, that is 1.6 into 0.78 multiply within bracket S of C plus S of H. To simplify this allowable stress, that is nothing but 1.25 bracket S C plus S of H. From this total stress range, SH is a reverse for the longitudinal stress developed due to loading such as pressure, weight, and other sustained loadings, giving the allowable stress range for the flexibility, that is 1.25 into S to C plus 0.5 into SH. So the can calculate the allowable stress means it does not consider the excessive cycling conditions. The code allows means ASME 31.1 and ASME 31.3 allows the stress range reduction factor according to clause 102.3 and ASME 31.3 in clause 302.3.5 specify the allowable expansion stress range. So here they are defined the allowable stress range, that is SA equals to F in bracket 1.25 to SA plus S plus 0.25 into SH. So here where SA is nothing but allowable expansion stress range and SE we call the basic allowable stress at minimum metal temperature during the displacement cycle under analysis. And SH stands for the basic allowable stress at maximum metal temperature during the displacement cyclic range. The value of SC and SH are available in table A1 of the code ASME 31.1 and ASME code 31.3. So we can find out kind of their maximum allowable stress range through this codes, and we can consider their appropriate range. So here F is can consider the stress range reduction factor for displacement cyclic condition for the total number of cycles or the expected lives. Now, factor F has a value of 1.0 for situation where total number of cycle is 7,000 or less. This represents one cycle per day for nearly 20 years, which is a common design parameter. Further, if we look at endurance curve for carbon steels and low alloy steel available in the ASME section, that is 8 and division 2, if you see the handbook of piping design. So in this section, you see their costs for alloy steel and carbon steels. Might be you are studied their endurance curves in metallurgy science for carbon steel as well as low alloy steels. And this code means here if you have considered their cycles for SC and SH limitation intersects the fatigue curves and it gives different stress range reduction factors. We have to consider different parameters wherever we have to consider. For this purpose, we have to consider the stress range reduction factors. So through this reduction range factors, so we can consider their appropriate values in the design parameters. Wherever we have to consider the piping design parameters. For this purpose, we have to consider different factors where we can analyze their range. For this, we have to consider that particular range. Just a minute, I will show you the table where we are considered the different ranges. Is it visible? Yes. Is it visible to everyone?
Yes, sir.
Okay. Here we'll see the stress range reduction factors. So here, if you are considered cycles and factors, if it is 7,000 or less, then we will consider factor that is 1.0, and over 7,000 to 14,000 go for zero point 0.9. So likewise, we can consider number of cycles from 7 lakhs. So onwards, we have to consider kind of 2 lakh to 7 lakhs, that is zero point 0.4. So this way, we can consider there's different ranges. This applies essentially to non-corroded piping systems. Corrosion can decrease the cycle lives. Therefore, corrosion-resistant material should be considered where large number of stress cycle is anticipated. The stress range reduction factor, that is F, can also be calculated by using the different relations. Now we'll see which relation we have to use and to calculate the stress range factors. So with the help of this relation, we can calculate the stress range reduction factor. F equals to 6.0 into n raised to minus 0.2 less than equal to 1.0. Here where n is equivalent number of full displacement cycles during the expected service life of piping systems. Means, as per the code, the designer that fatigue life of material operated at elevated temperature may be reduced. When the computed stress range varies, whether from thermal expansion or other condition, that is, we can consider the S of E is defined the greater computed displacement stress range and The value of n such cases can be calculated considering the n equals to here n of a plus summation comma into n for I equals to here 1, 2, 3 and so on, where Ni, where number of cycles of maximum computed displacement stress range, and comma equals to Si over Sa. So here Si, any computed displacement stress range smaller than Sa. That is Ni, where number of cycles associated with displacement stress range. So we can calculate the fatigue reduction factor F. It's called as a stress range reduction factors. Then, the help of this relation, we can calculate the stress reduction factors, or we can pick the data for factor through ASMEB 31.1 and ASMEB 31.3. From these two codes and section 8, we can pick the data as per the cycles from 7,000 or less. Onwards, we can pick their appropriate range. Now, here discuss about the stress range reduction factors. So up till now, do you have any questions, any doubts? So we can discuss. Yes. Do you have any questions, Harshal, Ritvik, Amar, Prabhu? Yes. Pratik. Yes. Anyone? Any questions?
No, sir.
Okay, fine. Then we'll close this session here and we'll continue in next session. Okay, fine. And so as concern